Roland Larsson is my name. This is a short video about the origin of wear. It's a kind of introduction to the topic of wear. That means that two surfaces come into contact. What may happen? When will wear take place and why? So let's go. Two questions we're going to try to answer are the following. What is the original wear and why is wear occurring? And as always, I think it's very good if you sit back yourself and think about this for a while before I'm trying to tell the answers. So please stop the video and think about it for a few minutes. Before describing different wear processes, I want to repeat some things. I'll start with the tribo-system. The tribo-system is comprising four elements. It's the one surface, it's a second surface, it's some kind of a third element, which is the medium in between the surfaces. It could be a gas, a fluid, particles, wear debris, dust from outside, and the fourth element is the surrounding itself, so different atmospheres, for example. On top of the surface you normally also grow some layers. We call them tribo layers when they have occurred during the wear process or rubbing process. Can also be oxide layers, for example, which are almost always present on any surface. Important parameters for wear are the following. So the material, of course, the different types of material and the microstructure of the materials. So one parameter that is especially important is the hardness, which is proportional to the yield strength of the material. The stronger the material is, the normally it's more wear resistant. It's also about how, if there are cracks in the surface layers, so if you have some impurities in the material that could where different cracks could start propagating from. The operating conditions are of course also very important. I mean, how high the load is, the speeds, how high the sliding speed is, if you have vibrations there, and etc. Temperature is important, definitely, and again the fourth element, the surrounding environment. If you are in a corrosive environment, for example, you may increase the wear rate. Coming back to that later. Surface roughness plays a role here because surface roughness also creates the kind of contact conditions, the contact mechanics of the surfaces. Surface roughness determines the local stress concentrations, and of that reason surface roughness is important here. And finally, I also want to bring up friction. Even if it's a little bit, friction is an effect of the parameters I mentioned here already, but friction itself will also influence the wear rate. The higher the friction is, the higher the stresses on the surfaces will be, so most likely the wear rate will also be higher when friction increases. So, as with friction, I must start telling you this, and this is very important, of course. Wear resistance, or the processes of wear, is not a material property. It's same as with friction. One material, one surface cannot have a certain friction. One material, one surface doesn't have a certain wear resistance or wear rate. It's very system dependent. It depends on the other surface and what properties that surface have. So and there are so many parameters influencing wear. It's so of the same reason as friction can't be predicted normally. Wear is also very, very difficult to predict. I also want to remind you that about the surface layers on that are normally present in a and that you need to be aware of when we discuss wear problems. If you start with a base material which is not influenced at all, well, the part of the base material that isn't influenced of the wear processes or the contact mechanics processes going on the surface, on top of that you have a worked layer which could be a number of micrometers. Here you have actually an effect of what has happened on the surface, not only the wear process but also the manufacturing processes making the surface. You have very close to the top layer you have a very, very much worked layer which could have been melted during manufacturing, for example. And that's normally pretty thin, as you see here. And on top of that you may have an oxide layer coming from the oxidation of the top layer when that layer meets the atmosphere, for example. And you may have some other react layer. If in a lubricated contact, for example, you may react something with the lubricant. Parts of the lubricant, the additives, may react with the oxide layer and form an additional layer on top of that. And finally, you may have some physically adsorbed layer. Could be some greasy molecules sitting on the very top of the surface. And then you have the surrounding gas or fluid. So this picture is very good to keep in mind when we discuss wear processes. I also want to remind you about the contact mechanics. There is a difference between rough surfaces contacts and smooth surfaces contact. If you have a rough surface, there is a smaller area of contact or smaller real area of contact, so the actual place where the asperities touch the other surface. And if this one, the rough surface, is hard, and then it will penetrate into this softer surface. And when you then slide the lower surface here relative to the upper surface, you will abrasively wear off material on the surface. You will plastically deform it, you will plow it or cut it away. So that's a kind of abrasive wear process, as well as it also becomes an abrasive friction process. If you have pretty smooth surfaces, on the other hand, you have a larger area of contact. So the two surfaces have big real area of contact. And then, since the surfaces come very close to each other, adhesive effects will be important. So the atoms, there will be an interaction between atoms on one surface and the other surface. And if this surface, real area of surface, real contact area is big enough, you may have so strong forces that you rip off material from one side to the other one. And that creates an adhesive wear and also adhesive friction. So this is also important to remember. In previous videos about the contact mechanics and also friction, I normally bring up this problem. If you have two surfaces, one may be soft, one may be hard, one may be smooth, one may be rough. What is the best combination? Well, if for example in this example you have a smooth, soft in contact with a rough, hard. Well, as I just previously, just a few minutes ago, I said this is not very good because the rough, hard will penetrate into the soft one and you may have a lot of abrasive wear. In the middle case here, you have a smooth, soft in contact with a smooth, hard. Well, that will mean that you deform the surfaces pretty much when you put them in contact under load, and you form a relatively big area of contact, and when you start sliding one relative to the other one, you may have strong adhesive forces and you may have a lot of adhesive wear. So that's not a very good case either. And as you may expect, the third case is then the best one, since you then have a rough, soft, you have a smooth, hard. That means that the smooth, hard will not penetrate into the rough, into the softer one, because there are no sharp asperities on that one. So you can't really create much abrasive wear, abrasive effects. On the other hand, there is a roughness on the soft one, so you create not too big areas of contact here. So the adhesive component will also be minimized. So this is kind of a tribological design you can think about if you aim at finding a wear resistant case and also a pretty low friction. Now let's say a few words more about adhesive wear. We normally distinguish between two types of adhesive wear. The mild one, where you only wear the layers. Normally you do create some kind of layers on the surfaces. That could be an oxide layer. Let's assume that we don't have any lubricant around here. We have some oxide layers formed on the surfaces, and when one of the surfaces move relative to the other one, you may wear the oxide itself. But then, if there is sufficient time, the layer will grow back again. So it will kind of self-heal. And there is, of course, a wear because you make use of the base material and you slowly corrode the surface. But this is a controlled process. It's a mild corrosive process, and it's a mild wear process. So this is a very beneficial case. Of course, you want to avoid wear in general, but this maybe in some cases, well, most cases, you can't avoid it completely. So this is a beneficial type of wear in that way. The other extreme of adhesive wear is the severe adhesive wear. Then you have so much wear of the protecting oxide layer that it wears off, and you penetrate through the layer, and the metals come into contact. And then you may have different types of adhesive or different severity of the adhesive wear. For example, if only this takes place on the asperity level, you get something named scuffing. So you have some kind of micro welding of the. If this is two asperities, the two asperities micro weld, and then when sliding takes place, they are ripped off, and you have some damage of the asperity of the surface. You may also have a complete failure of the layers here, so you seize the whole surface. So you have a seizure, global seizure, and then we call it seizure, and this is very bad, of course. Then you in both cases you have so much wear that you may not be able to use the surface anymore after that. The important parameters for adhesive wear are speed and motion. So normally the higher the speed is, the more heat, the more risk of wearing off the layers and creating a contact between base materials. The contact pressure, always bad. Surface roughness, well, if it's too smooth, as I said before, it shouldn't be too smooth. But if it's too rough, you may come into abrasive type of wear. So surface roughness is something to find an optimum here. And of course the types of layer you can grow on the surface. That depends on the atmosphere. If you don't have any atmosphere, like in space, this is a big problem in space, because then you can't grow back any oxide layer, and you may have seizure directly of mechanisms operating in space, and that is a big problem also, even if the number of mechanisms are limited, of course. The type of materials is also important here, and also the material pair itself. If you remember from other videos on friction, for example, adhesive friction, the material pair, the different materials are, now I'm talking about metals mainly, they are more or less compatible to each other, and some metals, for example, iron and aluminium, they are pretty much compatible, so they like each other and they may join each other easily if they come into contact. So if you don't want to have that, you shouldn't use iron together with aluminium. You may use it with some other metal combination like brass. Abrasive wear then. We normally distinguish between two-body abrasive wear, which means that one surface, like the asperities on one surface, plow or cuts the other surface, while three-body abrasive wear means that you have a third body. That could be particles coming from outside, like dust particles, sand particles. It could also be wear debris could come from an adhesive wear process that has taken place earlier, or it could be abrasive wear particles that further accelerates the abrasive wear process itself. In this case, surface roughness. Surface roughness is an important parameter, of course, because especially if a rough, hard surface comes into contact with the smooth, soft surface. So hardness itself is also important here. The harder the material is, the less risk for abrasive wear. So it's important to keep the system clean here, because if you can keep particles from outside away from the contact, then you increase you reduce the risk for abrasive wear. And of course also you should avoid the wear itself, because that could accelerate it. And then also it's a matter of the particle shape and hardness. So the particle properties that's also important. For example, if you have talking about sand particles, which could be pretty sharp and hard, they are normally a problem for metal surfaces. How to design for low wear then? Well, as I've already been saying here, you should avoid having similar materials. Sometimes you can't do that, but in a sliding contact, try to avoid having the same materials, and especially materials that are pretty much compatible to each other. You may put some coatings on that passivates the surface or makes it less easy to form adhesive bonds to the other surface. You may have two hard surfaces also in this case, also for adhesive wear, because then you keep the real area of contact small. And as I said about roughness, if you make it too smooth, it's a big risk of adhesive wear. On the other hand, if you make it too rough, you may end up into abrasive wear. You should have a good growth of the tribo film, but of course not that good growth that you corrode the surface. So this is also a balance, and the last bullet here, lubricant with additives, is also good, because additives may help you to form a tribo film that is worn instead of the base material. So but again, some of those additives are corrosive and they may corrode the surface faster than you want. So it's also again a kind of trade-off. You must have it sufficiently corrosive but not too corrosive. To avoid abrasive wear then, well, it's very good to have similar hardness, because then the surfaces will not penetrate into each other and they can't plow or cut the other surface. And of course also if you have high hardness on both surfaces, you also reduce the risk of plastic deformation, because abrasive wear is about plastic deformation. You may put coatings on here to make the surface layer harder. The harder surface, if you can't keep the same hardness on both surfaces, then you should try to keep the harder surface as smooth as possible. And as I said before, keep particles away. And of course, lubrication is a good way to do it too. I've been talking about layers here relatively often, and corrosion. I have mentioned the word corrosion a number of times. I should then also say that there is a wear mode called corrosive wear or tribo-chemical wear, and that is when you grow, depending on the atmosphere and what fluid you have around this surface or the temperatures. If you have, for example, very high temperature, many processes takes place at 500 or even 1000 degrees Celsius, and that increases the oxidation of the surfaces, and you form layers. It could be an oxide layer, and they grow more and more until they have reached some kind of critical thickness. And then if you put a surface in contact and move that surface, slide that surface on the oxide layer, you may damage the oxide layer and remove it completely, and the process will start again. And during the oxidation, you do of course consume the base material down here. And so it's a wear process itself. So if you wear off the formed oxide layer very rapidly here, you wear the surface very fast. So you can have a very fast wear process due to corrosion. But as I said, the mild wear, the wear of the oxide layer at least at room temperature or only 100 degrees or something in that range of temperature, it could be a good type of wear. It's a mild corrosive wear, but this, you don't talk about corrosive wear until it becomes a problem that you wear it off too rapidly. So it could also happen due to corrosive additives, which you need to add in certain applications like gearboxes, where you have a lot of sliding in high load, high sliding speed. Then you need to form stronger layers than the oxide layers, but that again is a kind of corrosive process. So you must have a kind of balance. It mustn't be too corrosive. And that is what I mentioned here now was the EP additive I especially refer to. And the EP additive is a sulfur compound that reacts with the surface normally, and this goes faster than the oxygen may do it. So as I said, in a gearbox, the oxide layer formation isn't fast enough to create this tribo film, so you really need to have a faster one. So, but this is, as I said, it's a corrosive process, but still, it's always a trade-off, which is you can see many times in life. you have to choose between two bad things. So instead of having a very severe adhesive wear like scuffing or seizure, you get corrosion instead. But that could be better, because scuffing and seizure is of course end of life of the surface. What can you do to avoid corrosive wear? Well, you have an atmosphere that isn't increasing the corrosion processes. That also includes temperature, that you keep temperatures down if possible, and surface reactive, or the chemical reactivity of the surfaces should be low as possible. That's a way. The choice of material is important there, of course. And to repeat it a third or fourth time, there should be some corrosive wear, because otherwise you may end up in scuffing if you don't form a new protective layer when wear has taken place. Coatings of different types can help to passivate the surfaces and then also reduce the corrosion of the surface. So that is all for the basic part of the wear. So let's continue with other videos about wear now. Thank you very much.